I usually like to start out by explaining a bit about why this course exists. You're all graduate electrical engineers or equivalent, and this is an analog course, and the material is pretty basic, and you may wonder why it's worth your while to be here, because you've all had at least one course in this stuff, probably more than that. And the premise for this course is that I suspect you may have found out that in the real world where you are now doing a job, not very much of what you learned in school has turned out to be much use. Well, I see a response there already. That's good, because that's what this course is about. There's another part to that answer, though, and that is, if most of the stuff you learned in school, taught by professors, turned out not to be much use, why are you here listening to another professor talking about the same old stuff again? So I want to try to answer both parts of that, which is really the explanation of why I hope this course will be useful to you. Because yes, indeed, the material is pretty basic, and in fact most of it you will recognize, but I think you will find that the perspective is quite a bit different from what you will have had before. But in addition to that, there will be a little bit of new stuff, which I'll describe in a moment. But the thing that's different is the perspective, the approach, which is really to do with the motivation for why are these methods and techniques going to be useful to you, which I hope they will, and that's really why we're all here. To lead into that, I tell a little story which fills out perhaps why, or at least the reason why, some of these things that you learned in school turned out not to be very much use. If you look at this very qualitative little diagram, what this is supposed to indicate is that during your university time, you have a pretty rapid intake of information. The students at Caltech that I teach all the time commonly say that it's like drinking from a fire hose. So there's a lot of stuff that goes in very fast. And then when you get out into your first job, it's like falling off a cliff, because suddenly the context and the environment is totally different. And often what happens is, out in your first job, you get a set of specifications that's put on your desk by your new boss, who rushes by in a hurry, of course. And he says on the way by, we have to respond to this RFP next week. Get with it. So you start thumbing through this big sheaf of papers looking for the technical specifications. You can't find any. It's all boilerplate, or so it seems. Deliverables and the timetable and the schedule and the budget, and eventually maybe in section 5.8.1.3 you find the technical specifications. Maybe a couple of pages worth. Not very much. And since we're talking about linear systems at the moment, let's say the specification is to do with an amplifier. Well, there's not much you can say about it, is it? It's got to have a gain of so-and-so, certain frequency response, certain input and output impedances, dynamic range, works from a certain power supply. And there's not much more to it than that, really, as far as the electrical specifications are concerned. There's a whole lot of pages to do with things like fungus test and all that, but your job as an electrical engineer is to meet these electrical specifications. So you start looking through this list, and you begin to have a terrible sinking feeling. Where do I start? Because this is backwards from everything that you've done up to this point in school. In school, you're given a circuit, given most of the values probably, and all you have to do is the analysis. You've got to work out what it does. And when you've finished the algebra and you get this long equation. That's the answer. Finish the job. But this is the first thing you notice now about real life. It's backwards. Because the specification is the beginning of the design problem that you now have to do, but it is the answer to the analysis problem, which is what you know how to do. And this reversal of the order of things is really the first major realization you have when you're out there in the real world. And the design job is to work backwards from that specification to the beginning, which is what circuit configuration to use and what values to choose for the elements. So now you have this sinking feeling, because you don't know where to begin. There's no circuit diagram. So maybe you ask the fellow at the next desk. He's been there a little longer than you have, and he says, well, we had a job like this not too long ago. Why don't you look up the documentation for that? And so you get that out, and it's not one piece of paper, and that's not much help either. But that one piece of paper probably is the blueprint, the circuit diagram. It has everything on it. And so now you feel a little better, because there's some circuit, even though a lot of it is little boxes with part numbers that don't tell you much about what's inside. But anyway, at least there's a circuit there. Good. Now you know where to start, because now you can write a lot of equations. That's the objective, isn't it? That's always the first thing you do, is write down all the equations you can think of. So you start that, and then you start doing the algebra. But this feeling of euphoria doesn't last very long, because pretty soon the equations keep getting longer and longer. And by the time you're at the bottom of page 2, the equation is slopping over into the next line. And it's getting worse and worse. And it's much worse than any problem that you practice doing as a student, because the circuit is much more complicated than any of these simplified, sanitized little examples that you were given before. There was a good reason for that, of course. Most classes are very large. Most of the homeworks and exams in courses are graded by graduate students who don't know very much more about it than you did at that point. And so there has to be one correct answer, and all the others have to be wrong. So the problem has to be set up in that way. So that's pretty much unavoidable on the large scale, but of course the real circuit is much more complicated than that. And that's why the equations get out of hand much quicker, and why, before you've done more than a page or two, the algebra goes into paralysis. There's nothing more you can do with it. So sinking feeling comes on again. So now what to do? Well, the algebra didn't work, so at least we got the circuit diagram, and let's have the technician go into the lab and put together a breadboard. Then we can fire it up, and we know it's not the same specification as this new job, but we can start twiddling things until it meets the new spec. So you go into the lab, or you send your technician into the lab, and now you can feel good for quite a lot longer, because it takes the technician quite a while to build it and get it fired up. So then you go into the lab with the technician and turn it on, and then you have another rather depressing realization. The technician knows a lot more than you do. He's very good at debugging in particular, because something isn't working right. He knows what's wrong. So you start learning a different way of doing things. In particular, you start learning that these ideal devices that you've analyzed and manipulated on paper really aren't ideal at all. Capacitors sometimes look like resistors, even inductors. Transistors make very good fuses. And so you start learning about the practicalities. And of course, the circuit that you have on the bench isn't meeting the new specifications, so you start changing some values until things begin to shape up. And now, as far as the story is concerned, the time scale now is going to get compressed a whole lot, because this is the beginning of a new way of learning how to do design. The knob twiddling, empirical, seat of the pants way of doing design. And after some months and years down the road, you can get to be a pretty good designer. Now, I hope this story sounds a little familiar, even if it's exaggerated, of course. But that's really, I think, where most people find themselves. And maybe when you get to be pretty good at all this, you sit back sometime and think about what happened to all that academic stuff. And that's when you realize you didn't use very much of it. And that's too bad, because it really is useful and it can be useful. And that's not saying that all the practical things you learned were a waste of time. Of course, that's not true. They are valuable and important, in fact, just as important as the academic stuff. So I'm not saying that's not a good thing to do. What I am saying is that you can do even better if you can translate the academic stuff in addition to learning the practical aspects, because the combination of the two is what is really powerful. So, to go back to this diagram again, what this is supposed to represent is that you've had this force feeding for your university career, and then you drop off this cliff where you suddenly discover not much of it is usable after that first time when you got bogged down in the algebra and gave it up, and then you never went back to it. Didn't work the first time, and you never have time again to go back and see what to do with it. So you start this much slower and longer process. And that's how you eventually become a good designer. Now, that's, I think, I hope, answered the first question about what this course is about. But the second question is, why is another professor going to be any different from any of the others? That's where that story continues a little bit. Because what happens very often is that something goes wrong down the line as far as the product's concerned, usually when it's in production or about to be in production. And then the consultant gets a telephone call. And this is where professors get into it, because that's how professors make a real living, you see, is by doing consulting. So a panic phone call comes in. We had to stop the line because some of the units are oscillating. Please come and fix it. So the consultant rushes down immediately, and the first thing the consultant does is say, well, let me see the documentation. Well, there isn't any except this scruffy page in a notebook, but he didn't put down everything there. It reminds me of a little comment that Bob Pease makes. Bob Pease is an experienced analog designer with National Semiconductor. You may have seen some of his writings, and one comment he makes is, which I think he calls this Mulligan's Law, that when you see something funny on the bench, write down the amount of funny. And that's a good policy, because even if you don't understand what's going on, it's certainly good to make a detailed note of it, so maybe you can understand why. Anyway, there isn't much written down usually, so the consultant doesn't have much to find. So then he says, well, let me talk to the design engineer. Oh, he isn't with the company any longer. So then you have to do some reverse engineering from a unit that isn't working to find out how it was supposed to work. And if the consultant is lucky, He may come up with some suggestions about how to improve the design. So then he goes and tells the project manager. Then the consultant learns something new. Because the project manager says, oh, we can't do that. It's too late. All the PC boards are made up. All the parts inventory is in. We can't put any extra components in. And so it turns out what the project manager wanted from the consultant was not a corrected design. What he wanted was the magic wand waved over it. Make it work, but don't change anything. So the consultant is reduced to the empirical design approach also. Twiddle things, change some values, that's as much as you're allowed to do. So it's a patch-up job again. Now, I did this for a long time. And this sort of consulting is putting out fires. And it's always at the last minute, it's always a rush job. And at first, I kept thinking, this wasn't a very good design in the first place, so it's kind of hard to fix it, especially by patching it up. So I sort of implicitly blamed the design engineer for doing a lousy job. But eventually I came to the realization it's not the engineer's fault. It's my fault. Or professors in general, anyway. Because many of the things that we find out in the design are things that simply shouldn't have happened. And it's our fault if we didn't teach the students any better than we did. So this is what led to an evolution and a change of the way that I taught this stuff. Originally I did it the same way as everyone else. You have a textbook and you go through certain chapters in a certain length of time, and you have to get to the end of it in time, regardless of whether you had to leave something out or not. But it was 90% analysis. Here's the problem, and here's the method of solution to get the answer, and the answer is an equation, which says the gain equals whatever. And it has to be unique, only one correct, of course. But this is part of the design problem, but only a part of it. And yet you spend 90% of your academic time doing this kind of problem. And it's not only that it's all analysis, but you even know which method of analysis that you have to use. It's the one you had in the lecture last week, because this is the one you have in the homework problem this week. So you don't even get to make any choice or make any evaluation of what relative merits of different approaches may be. So what began to change in my own course was, let's shift the emphasis from the detailed material to the methods. What's the approach? How are we going to go about making the stuff that we do in analysis useful for design? This gets now to the actual methodology, so I want to say a few things now about the design process itself. This is a very qualitative little diagram. I'm going to refer to it several times as we go through all this. The design of a product or a system starts at the left-hand end of this picture, and you notice that the horizontal axis is labeled in two different directions: accuracy from left to right, simplicity going the other way. You start a design project somewhere over at the left with a very simple model, which therefore isn't very accurate, probably a block diagram. And then you consider how many blocks you need to achieve the various functions. So the first part of the design is essentially just assembling some of these little blocks. Then you probably have an iteration to do. That is, you change your mind. which is like taking one step back in order to take two more steps forward. You could call this a design analysis iteration cycle. Now, you may begin to write a few equations, but they're not really equations to be solved. They're just quantitative relationships to see whether you're in the right ballpark, whether you have enough amplifier stages to achieve the total gain you need, for example. And there may be several of these iterations as you go through the design cycle. But notice that the objective is to progress gradually from left to right in this picture. That is, the model that you deal with gets gradually more complex because it's going to become more accurate as you go along, even though there'll be steps back to be taken now and again. In particular, there's one crucial iteration point that will come up, which is when you've progressed with your paper design to the point where you think you're close enough to the answer that it's time to breadboard it or simulate it or at least find some way of verifying what you've done up to that point. Ideally, this is a measurement on the bench for a breadboard. Typically what happens is that when you make some measurements, some of the measurements will agree with the prediction and some of them won't. Those that agree, of course, means that you've taken the step forward that you can retain. Those that don't agree with the prediction fall into two different classes. One class is the one that you're familiar with already. There was something wrong with the measurement. The probe wasn't hooked to what you thought it was, something's out of range, something's overloaded, something's wrong somewhere in the measurement scheme. So you dispose of all those one by one in the usual way. But then there's the other class that's left, which is that now the measurements probably are correct, that's what the system is doing, but it's not what you thought it was going to do. Or it doesn't meet the specs yet anyway. This is a reason now for the iteration again. Now you have to take this step back and you have to modify the model somewhere, and then you repeat measurements, and more of them agree with the prediction now, and there may still be some discrepancies requiring yet another iteration. So there may be several of those iteration loops to be followed as you go through the design. Then the next step in the process is you have to choose a termination point, which is not necessarily all the way to the right-hand side of this picture. That's an asymptotic limit that you can't achieve anyway, because you're never going to get a 100% exact model. But the important point about this is that you have a design trade-off to make in choosing that termination point. And that's determined to a large extent by the relationship between the specifications of your system relative to the tolerances of the components that you're going to use. Also, it's to do with what is the overall nature of the application. If you're designing something that's going to go into a spacecraft, obviously you have to go much further towards the right-hand end of this picture than you do if it's a low-cost commercial product that doesn't have to operate unattended for long periods of time. Because part of the design trade-offs that you have to take into account is the economics of it. These trade-offs are not all technical. Many of them are economic as well. And of course, you've often heard it said that project managers have a lot of trouble getting their engineers to stop designing. They never want to give it up until it's just a little bit better and I can do better here. But the project manager has to impose a termination simply for economic reasons. So a lot of things enter into the choice of the termination point. The important thing is that you need to recognize that and make an optimum choice and not just let it happen. So this is the overall structure of a design project. And I've mentioned already that you need to make a gradual progression from left to right, which means don't try to take too big a step at a time, because then the number of discrepancies between measurement and prediction is going to be larger, and it's going to be more difficult and in fact take longer to go back and sort them out. This is a good place to mention also the use of computers, CAD. There's a tendency nowadays, especially in large companies, to plunk a workstation in front of every design engineer, which is very nice of management to do that. But it can also be brought into play too soon. Because the tendency is to put the whole design into the computer all at once. That is, you try to get the computer to do your thinking for you. And it isn't very good at doing that. So, one important thing to bear in mind, when you have a computer, you ought to know what to expect from the computer before you put the circuit in there, at least qualitatively. Just as you ought to know what to expect before you go to the bench and start putting the system together. On the bench, you know very well that if you spend half a day taking a whole lot of measurements, and then you go back to your desk, and the very moment you start to look at what the measurements are telling you, you know the whole thing's worthless because something wasn't working right. So you wasted all that time because you didn't know what to expect before you started. The same thing is true with a computer, but a little more subtly, because you have to get over this reliance on the computer that what it tells you is always right. It isn't. And it's not always right for reasons other than the well-known one, which is garbage in, garbage out. Because unfortunately the computer can give you garbage out even though you put the good stuff in. And sometimes you tend to forget that. It's true, computers don't make mistakes in the sense that you make paper mistakes when you're doing computations or arithmetic, but they make other kinds of mistake, depending on the algorithm that is programmed into them to solve the problem. I'm sure you're actually well aware of this because you've probably taken courses in numerical analysis, which deals specifically with that sort of problem, which is to avoid computational error from creeping in and degrading the result, sometimes even to the point where the result is totally useless. And it's hard to remember that sometimes when you have these very powerful workstations that seemingly can work out these immensely complex problems very quickly. Well, they can do that very quickly, but you still have to look at the answer critically to see whether it really is doing the right thing. And we'll see some examples of that on a very small scale and apparently very simple little problems. But they turn out to be quite important even with pocket calculators. So that's an important thing that we're going to look into. Anyway, the point about this diagram is that all of the things I'm going to be talking about in this course are related to different parts of this picture. That's why I'll be referring back to it fairly frequently as we go through this process. There's a little bit extra still to put into this picture, which is the emphasis is mostly on the design engineer, but he's part of a team. And the project manager is responsible for guiding that team, especially for making sure that the time scale is proper and the economic part of the trade-offs get into it as well. Often there is a design review committee also, which is people from other departments or maybe even outside the company who are asked to come in, and the design team, the working team, has to make a report to the design review committee. And the report is partly written usually and maybe partly oral in a presentation. Now, how is the design review committee going to do the maximum good job? The documentation and the presentation has to be specific and complete. The way the results are presented has to be immediately interpretable. not just some long equation. Because if the results presented are not detailed enough, or if it's in obscure equations, all the design review committee is able to do is to say to the design engineer, well, it looks as though it's coming along all right, carry on. And this is after the design engineer has probably made a report such as, well, it seems to be working at least over part of the operating range. And that's very fuzzy, you see, and it doesn't help the design review committee to be any help. So part of what I want to talk about is not only how to do these analyses and how to proceed with the design, but also how to present the results so that maximum information can be obtained from them. Now let's look at one of these iteration loops in particular. I've labeled different pieces of it now. Analysis is the thing that comes first. And so what I'm going to be talking about mostly is analysis, but it's going to be a special kind of analysis. And I have a special phrase for it, which I'm going to be using all the time. That is design-oriented analysis. It's the only kind of analysis that's worth bothering with. Any other kind of analysis simply leads to a huge equation, which is useless. What are you going to do with it? And this leads to a very important point. An equation for the gain of a system, or whatever it may be, is of the form the gain equals. So the gain is the thing on the left-hand side, and on the other side of the equals is a huge fraction with all the circuit elements in it. So what have you got? One equation, and how many of those quantities are known and how many of them are unknown? One quantity is known, which is the answer, the specification. All the other quantities are unknown. That's the object of your design. So you have one equation and 45 unknowns. No wonder you think the analysis hasn't been much value in your design career. Because very early on in your life, the mathematicians told us you have to have as many equations as you have unknowns that you need to solve for. And here, in the real life problem, you haven't anywhere near enough equations to solve for the number of unknowns. So you start from what looks like a negative position. It's an insoluble problem, according to the mathematicians. Well, the problem is, the trouble with that is that the mathematicians are the guys who get to us first, not the engineers. See, the engineers have to solve the problem. And if they weren't told to begin with that it was impossible, they'd have a lot better chance of learning how to do it a lot sooner. Because they have to discard a lot of the things that we were all taught in the early days. Well, if we're going to solve an engineering design problem, what it amounts to is that instead of this one equation with 45 unknowns, we have to find some way to get additional equations. But they won't be exact equations. That is, they won't have the equal sign between the two sides. They will have trade-offs, approximations, and approximate equalities or inequalities. That's not perfect, but that's what we're going to have to live with if we're going to solve the engineering design problem. One of the first techniques that I want to talk to you about is how to get one equation to tell you more than one useful piece of information. That's quite possible, although it's contrary to what the mathematicians told us. But that's a good starting point. So that's one of the first things to think about. So added to this picture now is the objective of design-oriented analysis, the only kind of analysis worth doing. To get an analytic answer in a form which is going to be useful for design, you have to remember that design is the reverse of analysis, because the starting point of the design problem is the specification, and that's all you know, and that's the answer to the analysis problem. That means you need to do the analysis in a certain way. Now, because engineers always like to deal with diagrams, especially block diagrams, I've made one to illustrate that particular point. This is a typical progression through one of these iteration cycles. You start with the model, perhaps with a few tentative values or guesses, and you do your analysis, and you find a result. Then you compare that result with the specification. And of course, it probably won't agree. So there's a discrepancy. Now we can complete this block diagram and make it look like a little feedback loop. We compare the output, which is the result, with the specification, which is your reference, and then you use the error signal to correct the original analysis. And the key point to this is that in closing the feedback loop, which is what makes the output track the reference, which is your objective, that is to make the result agree with the specification, in order to do that, you have to be able to work the analysis in reverse. Otherwise, you can't close that loop. And that's the crucial thing in achieving a properly controlled design. So one of the characteristics of design-oriented analysis is it must be usable in the reverse direction. You have to be able to invert it, in a sense. Now here are some of the techniques of design-oriented analysis. And what I'm going to do for a little while now is go down this list and summarize those techniques, because this is what the next 3 days is going to be about, is going in more detail through these various topics. But I want to summarize them first, because the important part about the summary is the motivation. What is the reason why it's worth coming up with these techniques in the first place? This is the thing which unfortunately is too often missing in the formal academic methods. An instructor gets up there in front and says, well, this is how you do this problem. But why do you want to bother with that problem? Why is it worth thinking about? And why is this method better than any other way of doing it? This part of it often gets left out. So the important part of these techniques is, why are they useful? Because if they're not, well, don't bother learning them anyway. So that's the starting point. Now, look at this very first one here. Lowering the entropy of an expression. That doesn't mean anything to you. There's a new term in here, entropy. Now, that's not a new word, and that's the reason I've chosen that word, entropy. You've heard of it before from physics. But all you need to remember about it for this purpose is that entropy is a measure of disorder. The higher the entropy of a system, the more disorganized it is. We often heard, at least in the old days, that the universe is running down. Its entropy is rising. Eventually, when everything is at the same temperature, it will all stop. Now, that may not be the modern view of astronomers, but that doesn't matter. The point about entropy is, if you leave a system to itself, its entropy increases because its degree of order gets less. Entropy, as a matter of fact, also has a technical definition even in electronics. The communications theory people talk about the entropy of a communications channel. It's to do with the information content that it's capable of transmitting. But I'm going to use that word in a third connotation with a purely qualitative definition. The entropy of an expression is to do with the ordering of the terms in the expression. A high entropy expression is one in which the arrangement of the terms and the element symbols conveys no information other than what you can get by substituting a complete set of numbers into that equation. Now, when you think about how you usually do the analysis of a circuit diagram, you start with a circuit model and you write equations, maybe Kirchhoff's laws. You do your analysis to eliminate all the unknowns except the one you need, which is the answer for the gain. Everything on the right-hand side of that equation has got the information to do with the circuit elements and its configuration. And the arrangement of that stuff on the right-hand side is the way it comes out of the algebra of its own accord, which is a fraction whose numerator and denominator each is the sum of products of the various element values. Sums of products. And obviously, if the circuit has got a lot of elements in it, you get a lot of factors in each product, which is what makes that a very long equation. All that you can do with that equation is plug numbers in it. And you get one piece of information out, which is the answer for the gain, which isn't right. So the first thing you need to do with that equation is put some order into it. This is the objective of design-oriented analysis. It's to lower the entropy of that expression by putting some order and some grouping into the terms and the elements so that where they came from is more transparent. Maybe not totally transparent, but at least so you get a better idea of where they came from in the original circuit. Because only in that way can you use that result backwards, which is if you need to change some element values, then you need to know which ones are more important in affecting the answer and which ones are less important. But if the order in which they showed up in the result was random, just the way it came out of the algebra, you get no guidance in doing that, except by cut and try. So the important thing about a low entropy expression is putting some order into it, because only in that way can you close that feedback loop by working the analysis backwards, because you can see how the answer got constructed. That's the important thing. Here's a simple example of that we're going to go into in more detail pretty quickly. A very simple circuit, equivalent circuit model. You recognize what it is, I'm sure. This is a T model of a bipolar junction transistor. It's the small signal equivalent circuit relevant to a particular DC operating point. There's only two elements in the model. The collector current generator is beta times the base current, and the base emitter junction is represented by RE, which is the diode slope resistance. Outside the transistor, you have a bias divider collapsed into RB. We have an equivalent source, V1, source resistance RS, and we have a load resistance RL. Usually the most important analysis that you need to do about this circuit is to solve for the voltage gain. So I call that A sub M, M standing for mid-band, because no reactances are accounted for yet. So we want to solve for AM, which by definition is V2 over V1, the output voltage divided by the input voltage. You go through standard circuit analysis procedure, and this is the answer you get. Standard form, a fraction whose numerator and denominator each is the sum of products of the various circuit elements. And all you can do with that result is plug in numbers. Now, that's not much help. So right underneath that, I've written a low entropy version of the same thing. It's the identical result. But now, the grouping and the arrangement of the terms in that result tells you a whole lot more useful things for design purposes. For one thing, notice that in this denominator, it's a sum of resistances, one of which is already a parallel combination. So it represents a series parallel combination. And the thing you know about that is resistances in series are dominated by whichever one is larger. Resistances in parallel are dominated by whichever one is smaller. So if the numbers that you've chosen initially are not satisfactory, then you have a much better idea of how to go back and change them when you have the grouping already arranged in series parallel combinations, because you know which ones will be more important in the result. So that's just one example of the useful form of the lower entropy version of that result. Another example of lower entropy, another technique, in fact, of the design-oriented analysis is doing the algebra on the circuit diagram. Putting it in that way, notice, already implies that you want to avoid doing algebra. Right away, you notice this is the opposite objective from what you practiced as a student. It always seemed as though the objective of being a student was to do as much algebra as possible. But in real life, it's exactly the opposite. The less algebra you do, the more useful the result is going to be. So that's why this particular technique, doing the algebra on the circuit diagram, is really a way of avoiding algebra. And in this example, notice that all I've used is a very basic theorem, probably the first theorem you learn to do with linear circuits, Thevenin's theorem. You replace a linear circuit to the left of a pair of terminals by a Thevenin equivalent, which is a voltage source in series with an impedance. So everything to the left of the line I'm showing right here in the other diagram has been replaced by a Thevenin equivalent voltage source and a series impedance. Notice that in doing that, the number of loops is reduced. So when you do the algebra now on the right-hand diagram, you have only one equation to write instead of two. So the algebra is already simpler. So the reason I call this doing the algebra on the circuit diagram is that doing a circuit manipulation has actually cut out some of the separate algebraic process. Now notice that when you do circuit manipulation like this, the circuit elements get more complicated. But they get more complicated in the proper way, that is, low entropy way, because already you see immediately that this resistor is formed by these two in parallel, because that's how you derive that element. And so you retain it in that combination, using this symbol to represent parallel impedances. And that's another habit that you may need to reverse, because perhaps ordinarily, whenever you come up with a parallel combination, immediately you write it out, product over sum, R1 times R2 over R1 plus R2. That's throwing away useful information. Keep it in the compact parallel notation, because it tells you now which one is more important. So that's another example of a low entropy expression. You get it more directly by doing the algebra on the circuit diagram. Here's another way. Doing the algebra on the graph. Again, a way of avoiding doing algebra. This is a particular example we'll get to on Friday, almost at the end. For the moment, all I need to say about it is that this represents, in asymptote sketch form, the magnitude versus frequency of two different functions of complex frequency, using S as j omega, the usual format for representing frequency response in the frequency domain, or in the Laplace transform domain, really. So this function, which has two poles and a zero, is represented by the asymptote sketch at the top left. Then there's a separate function which represents the other set of asymptotes, magnitude function also. Suppose your algebraic objective is to add those two functions together, that is, to put a plus sign in between. If you try to do that algebraically, you see immediately you're going to be in trouble, because you have to cross multiply numerator and denominator of these two functions, and then you have to multiply out these factors of s and collect powers of s to give you a new polynomial, which you then have to refactor. And right away, you see, in this case, you're going to get a cubic equation. A cubic equation is bad news, algebraically. You remember about cubic equations, but not much. We all remember the quadratic equation, almost the first formula we ever learned. I'm going to have a few things to say about that too. But we all know the formula for the solution of a quadratic equation. We all know there is a formula for the solution of a cubic equation, but I bet you don't remember what it is. And I don't either. Because the first time you ever tried to use it, you found out that it was an implicit equation involving transcendental functions, and the only thing it was good for was plugging numbers in. There's nothing you could do with it analytically. So the first time you tried to use it, it wasn't any help, and you never used it again, which is sort of what happened to 90% of all the stuff that you learned. And that's the problem that we're fighting right now, you see, is how to get the value out of those things, which really means how do you keep them under control? How do you make them work for you? Well, in this example here, this is how you can find the analytic roots of a cubic equation without using that nasty formula that doesn't really give you analytic roots because it's implicit. How do you do it? Well, when you have sketch like this, you can see that if you're going to add these two functions together, remember that this is a double log scale. This is dB vertically versus frequency on a log scale horizontally. So it's really a double log scale. So whichever function is largest is certainly going to dominate the sum. So at relatively low frequencies down here, the left-hand function totally dominates the result. And the opposite is true if you go to high frequencies. Now the other function dominates the result. Notice we already know most of the solution. We know what it is at low frequencies, we know what it is at high frequencies. The only part we don't know is what happens during the region of changeover, which stays fuzzy. But that gives us the clue to how to simplify the problem. Because obviously these corner frequencies down here have nothing to do with what happens in the region of transition. So why not throw those frequencies away? They're not important in determining the only unknown part of the solution. So if you get rid of all of that, all you're left with is these two asymptotes, which is equivalent to throwing away the ones in these three factors. Because what you're saying is that for frequencies well beyond these corners, the S terms are going to dominate over all of the ones. So you just throw away the ones. Now you can solve the problem algebraically. Because when you do the cross multiplication of numerators and denominators, you still get S cubed, but you don't get a constant term. So you can factor out an s of the cubic equation, and you're left with a quadratic that you can handle also. And so you can get an analytic, that is symbolic, solution of the cubic equation, and this is what it is. I get this positioning just right. What happens when you add those two functions together and you make that restriction to solve for the only part you don't know? These are the three resulting factors of the cubic equation. Because once you've factored out the s and solved the remaining quadratic, that was the only part you didn't know, then you can put the ones back in again and restore the complete result. So this is the analytic solution, in which you actually have an analytic formula for this new quantity, the omega c, which is this intersection frequency. Now, that's the way an engineer solves real problems when the mathematician told you it couldn't be done. And the key to it, you see, is approximations. The mathematician, of course, strictly speaking, is correct. But the way you get around it is that you have to make appropriate approximations. And learning when and how to do that is really the skill of doing design. That's the important part of the design process. And that's what takes experience and practice to learn, really. That's where it's centered at, is making appropriate approximations. And that means assumptions as well. Here's another technique of design-oriented analysis. If you just look at the right-hand part of this picture, you recognize, and again this is asymptote form of magnitude versus log frequency. The picture on the top represents the normal pole, and that's represented by a 1 plus s term in the denominator. The bottom picture is a 0. It's a 1 plus s term in the numerator. Notice that the relationship between those two results is, algebraically, the s factor moves from denominator to numerator. Pictorially, it's an inversion of the diagram. It's turned upside down. And that follows, you see, directly because of the log scale of dB vertically. Because when you move a factor from the denominator to the numerator, that's the same as reversing the sign of the logarithm, because log 1 over x is equal to minus log x. So that's why that geometric relationship exists. Now, that's familiar. You know that relationship between poles and zeros. But the frequency axis is also a log scale. So the same principle applies. So notice that graphically, the left-hand pair of pictures is a horizontal reversal of the right-hand pair, which is analytically equivalent to inverting the s term, because the s is the horizontal variable. I should say frequency is, but this is a magnitude graph. So the relationship between these two pairs now is a horizontal reversal of the asymptote picture is equivalent to an inversion of the s terms, so you could call those an inverted pole and an inverted zero. And most people don't use this notation, which is okay. You can get by perfectly well without it. The point about inverted pole and zero representation is that why not take the advantage of the symmetry of the picture? Because very often what's important about frequency response is the flat part, which is the mid-band gain, for example. And certainly if you're talking about audio amplifiers usually are AC coupled. And so the specification is to do with the mid-band gain, and then you have coupling and bypass capacitors that are going to cause the gain to differ from that as you go towards lower frequencies. But the important thing is, where does that begin to happen as you go down in frequency? So the important part of the specification is the high frequency part of the diagram, not the low frequency part. So why not have the expression with the important part of the gain out front, and then the inverted pole and zero tell you how the gain is going to depart from that value as you go towards lower frequencies. And it's simply the reverse of what you normally do at high frequencies. So there's advantage to be gained in use of inverted pole and zero. And that carries through also to quadratic forms instead of linear forms. On the right-hand side, there's the usual double pole low-pass filter, represented by quadratic in frequency with a certain Q factor. And again, moving the entire quadratic from the denominator to the numerator gives you a quadratic pair of zeros corresponding to a vertical inversion of the asymptote diagram. But the same thing works if you reverse the frequency direction. Now the diagram reverses, and that is equivalent to inverting the S terms. Here's another important aspect of using numerical values to make analytic approximations. That we're getting down now to the nitty-gritty of where approximations become useful or even necessary. You start analyzing a certain diagram, and it gets to be complicated. So you look for ways to simplify the result. So with your tentative numerical values or your trial values that you've started with, you start looking for terms that may be negligible. And in this particular example, maybe for the values that you choose, you find out that this middle bracket, which is the sum of two terms, the numerical values may be such that the second one is negligible compared to the first. So you throw away that term. And this is normal procedure. Where the procedure now that I recommend deviates from the normal is that usually what happens is that having thrown away the term, you simply keep the numbers that you had for all the other ones in order to justify doing that, and then you continue to work the problem with the numerical values. But you've already now thrown away useful information, because the answer you get is a numerical answer. And then when you want to use it backwards for design, you've lost the origin of the terms. So you have to go back to the point where you drop that term and pick it up again, and it would be much more useful if you had the analytic terms in the answer the first time. So the recommendation is use numerical values to justify leaving something out partway through your analysis, but then, having thrown it away, restore the symbols for the rest of it and continue to work out the problem with the symbols so that you get the low entropy answer, which can be useful in reverse for design. Now, notice once again, this is the opposite of what most of us get taught. We get taught, don't make approximations unless you can justify it on the spot. Because if you do, and then you go back to symbols and you get the answer, and then you change the values later, you may invalidate the approximation that you made. So don't do that. Well, all of that statement is true except the last sentence. Do that. Because all you have to do is that if you do change the values later as part of your design iteration, then of course you do have to check that the approximation you made way back is still good. Now, the mathematician said, don't expose yourself to that possibility, but suppose you do. What can happen? Only one of two things. When you go back and check the approximation with a different set of numerical values, either the approximation is still okay, in which case you're home free, you finished. The other possibility is it wasn't okay. But the worst that can happen is, if it isn't okay, you have to go back and not make that approximation and continue without making it, in which case you're no worse off than if you hadn't tried it in the first place. But more than likely, you are going to be better off anyway because the approximation that didn't work might suggest a different one. So you've got value out of trying it even if it didn't work. So the main point about making unjustified approximations is you can't lose by trying. Because you can never be worse off than if you hadn't tried anyway. And more than likely you will be better off. So it's worth doing. That's another way in which engineers can get additional help in getting the more information that is needed to solve for the design problem. So in this particular example, which again is part of one we're going to go and do in detail, if the numbers that you've tentatively chosen suggest that you could throw away that term, throw it away, but keep the symbols in the rest of it and complete the analytic result. And the very next step to that is, you notice that the denominator of this expression is a quadratic in complex frequency, and it's still a quadratic even if you drop that term. So you know the quadratic is going to have two roots, which are the poles of this particular transfer function. And here's the sketch of that transfer function. These are the two poles, the omega 1 and the omega 3, which are the two roots of the quadratic equation. And I don't have to remind you where that comes from. You recognize that form instantly. It's got this nasty radical sign, and it has the alternative plus and minus. Now, I'm claiming that this is a high entropy expression, because you might as well not have bothered writing these symbols in there. You might as well have put the numbers in right away, because that's all you can do with it anyway. This expression doesn't give you any helpful information about the relative importance of these different terms. So my claim is that this is a high entropy expression. And what I want to show you a bit later on is a low entropy version, which are these two formulas at the bottom. And they look totally different, but they give you the same two answers, omega 1 and omega 3. And one thing jumps out at you immediately from the low entropy result. The two capacitors are separable. C1 determines this corner frequency, C2 determines the other. There is no interaction between the two. You would never know that if you looked at the high entropy conventional formula. It looks as though both capacitors determine both roots, which from a design point of view, remember that the answer that you know is the two corner frequencies. You have to pick numerical values to make those corners come out to meet the specification. And you see the conventional quadratic isn't going to help you do that at all. But the low entropy version is. Now, that's only one disadvantage of this conventional formula. There's another one. It has poor computational accuracy also for one of the roots, namely the one that involves this minus sign between the two terms. Because frequently the numerical value of the two terms to be subtracted is almost the same. And you end up subtracting two almost equal numbers. So that introduces computational inaccuracy, which means that you compute the two roots with different accuracies. And sometimes the accuracy of the poor one is so bad that the answer is essentially useless. And in fact, I'm going to follow up on that example when we get to this particular case. So we're a little way down this list now. I'll put that list back up again. And let's see where, it's the wrong one. Here it is. This is the list of the techniques that we're talking about. I mentioned lowering the entropy of an expression, doing the algebra on the circuit diagram, doing the algebra on the graph, using inverted poles and zeros, using numerical values to justify analytic approximations, And this is where we are now on the list. Now, the words I've used to describe those first ones are very qualitative. And you see, when we get further down the list, this word theorem has come in again. I don't like using the word theorem. That's off-putting. That immediately gives you this negative feeling it isn't going to be any real use. So that's why it's so important to emphasize the motivation for these things. So when I talk about the input-output impedance theorem, all I'm going to say about it right now in this introduction is, why is it a useful thing? Now, this is what the theorem looks like, and it's sort of obscure, isn't it? So let me drop that and just talk about why it's a good thing. Why do we need to know input and output impedances? Well, often that's part of the specification of the system. In fact, I mentioned that right at the very beginning. The gain is probably the most important thing, and so you do all of your analysis, which is the hard part of your design problem. Even if you use these shortcuts and all the rest of it, it's still where the bulk of the work resides in starting your designs, doing the analysis. So you do that for the gain, and then you start looking at the input and output impedances to see whether they need shaping up to meet specification as well. So how do you solve your circuit diagram for output impedance, for example? Well, you apply a signal at the output with a zero input, and you find out how much current goes into the output for a given voltage, or vice versa. In other words, you analyze the system all over again, from scratch, because you've got a different input and a different output than you had before. So even though the circuit model is the same, you do a different calculation starting from square one. And there's a lot of work in doing that, especially if the system has feedback. Because you know if you have feedback, whenever you push down at one point, it pops up all over. So the whole system gets into the act when you calculate output impedance if it has feedback. And the same thing with input impedance. A third, totally separate calculation starting from square one. You apply an input signal and you calculate how much input current goes in as a result, and that's how you find input impedance. So the standard way of approaching this is you do three independent, separate sets of calculation, each of which is about equally long in general. Now, you've probably done that quite a few times. And you may have noticed that when you do it the second and the third time, a lot of the internal sequences of algebra are familiar. They're similar to what they were when you did it the first time for the gain. And you begin to get the idea there ought to be a shortcut. There ought to be a way of not repeating the parts of this that are the same. But that's as far as you get, because how do you know which is the same and which isn't? So the idea passes away, and you have no choice but to go back and do it the hard way. That's what this theorem does. The theorem says, if you've done all the work to calculate the gain of the system, which is this quantity A, in order to find the output impedance, all you have to do is take these two simple limits with respect to the load impedance ZL. Remember, the load impedance is inside the A, because you already calculated the gain of the system with the load in place. So ZL is one of the quantities inside this expression for the A. And what the theorem says is, all you have to do is take these two simple limits and you get the output impedance. Looks pretty simple, doesn't it? It is. And the same thing is true for input impedance. The only difference is you take two simple limits with respect to the source impedance, which is also inside the A, because you solved for the gain with the source impedance in place. these two formulas are so simple that I can say that instead of doing 3 almost equally long pieces of algebra to find 3 results for A and ZO and ZI, by using this theorem, you do the work only once to find the A, and you save almost 2/3 of the original total, because the amount of work in doing this is almost negligible. And there's no better algebra than no algebra. So that's why those theorems are useful. Now, right below it on the picture is another theorem. This is also pretty general. And again, the important point about it is motivation. This is to do with the usual single loop feedback system represented by the conventional block diagram with a forward path amplifier and a feedback box. A is the gain of the forward path, K is the transmission of the feedback box. And again, this formula is very familiar. You recognize its format even if you use different symbols. What it says is the closed loop gain G of a single loop feedback system is equal to the open loop gain A divided by the feedback factor, where the feedback factor is 1 plus A times K, and A times K is the loop gain of the system, which has a symbol of its own, maybe the symbol T. That's the way we all learn it. And what we do when we're faced with analyzing a feedback system, we want to find the gains of those two boxes. So what do? We break the feedback path, usually at the output end of the box of the forward amplifier, as we unhook the feedback. That separates the two boxes, and then we calculate A and we calculate K, and we multiply the two together to find this denominator, and off we go. Well, unfortunately, the very first step of that turns out in practice often to be quite difficult, because the act of breaking the loop upsets the value of the A and maybe the K as well. In other words, there's an interaction between the two boxes which you could call a loading effect. So when you disconnect the feedback path, you actually change the forward gain because you've changed the loading at the output. So it may be easy to analyze your circuit diagram to find A, but the answer's wrong because it isn't the correct value that A has when the loop is in its normal closed loop condition. And exactly the same argument applies if you break the feedback path at the input, because the feedback path again often loads the input to the forward path. So if you calculate the gain with the feedback disconnected, again you get the wrong answer. So this sort of formula may be very convenient for, say, mechanical systems where there's a very clear separation between the plant, the forward path, and the feedback path. But in electronic amplifiers, very often that is not the case. So that's a difficulty of using the conventional expression. So what are we going to do about it? Well, this is well recognized, of course, and the way most of us get taught to handle it is we try to fudge the loading after you break the feedback path. You try to guess what the loading is, and you simulate it by putting a dummy load across the forward path, which is supposed to represent what the real feedback path does to it. And this may help. But if you really pursue that idea, again, you find yourself getting into fuzzy areas where you're not quite sure just how to represent that loading. So What I'm going to propose when we get to that point in the detailed solution is let's avoid breaking the loop anyway. But we don't need to know what A and K are separately. Because when you look at this expression, what is the quantity that ultimately we care about? It's the G, the closed loop quantity. That's what has to meet specifications. The customer for your design cares about G. He doesn't care about A. That's part of your job to design the A. But when you finish, no one else cares about it. That's got to be buried. Well, if it's not an important quantity in the answer, why don't we rearrange this expression to get rid of it? And it takes one very simple little modification. Multiply top and bottom of this expression by K. So now we have T over 1 plus T. And the quantity in front is 1 over K. And it has a very simple, direct physical interpretation by looking at the other factor. Suppose you could design a perfect feedback system that had infinite loop gain. T would go to infinity. G infinity, this new quantity, which is really just 1 over K, G infinity is therefore the ideal closed loop gain that you would get if you could build an ideal feedback system. And the useful thing about it is you know what it is because that's the specification. The only thing you know to begin with is G infinity. It's what you're aiming for. Now, what's left? If you already know what G infinity is, that allows you to design the feedback box right away. The only thing left to do is to make sure that the other factor is close enough to 1. Because you're not going to have infinite loop gain in your real system. So the design problem simply comes down to how do you design the system so that this other factor is close enough to 1. So the name I give to that is discrepancy factor. It's the discrepancy between the ideal limit, which you know, the specification, and what you're actually going to get in your real system. So that's a pretty simple objective, isn't it? To make that factor close enough to 1. Now actually there's two parts to that. It's pretty easy to make T large enough at some mid-band frequency. The hard part of it is that T is going to go to 0 eventually at infinite frequency in any practical system because the forward active gain is going to go to 0 because of shunt capacitance. So every real system has a gain that goes to 0 at infinite frequency. And of course if it's an AC coupled system, it's going to go to 0 at 0 frequency as well. So maybe at both ends of the frequency range, T is going to go away, which means this factor ultimately goes to 0 at both extremes. So the second part of the design problem, and this is really the difficult part, the second part of the design problem is keeping T large enough so that the discrepancy factor is close enough to 1 over the specified frequency range. That's the hard part. And there's a subsidiary problem as well that you already know about, which is how it goes away is important in determining stability against oscillation. But when you look at the whole problem reformulated, you see that the design problem from a feedback system now ignores the A. That's not what's important. There's only two quantities that are important, which is the G infinity and the T. The T contains A, but all that you need to know is the total product A times K. You don't need to know A separately. Which is very nice because A was the thing that was hard to find. So if it turns out to be easy to find T, and we've yet to look into that, that's really what the design problem is. So again, I called that a feedback theorem, although that's too high sounding a name for it, because it's too simple to deserve that name. But for want of anything better, that's it. Okay, now I can find one of my earlier pictures again. All of the techniques on the list so far we've done these two now, input-output impedance theorem and feedback theorem. All the list down to that point is to do with the analysis part of this iteration loop. Now we start getting around the corner. We get to how do we make measurements of these things. And the first thing to think about from the point of view of measurement is the loop gain is the single most important quantity of a feedback system. So we certainly want to find a method of measuring it directly. Not indirectly, but measuring directly the loop gain, so it's the principal result that comes out of the measurement. Now, the way that is usually done, again, is by breaking the loop. And where you break the loop, you apply a test signal, and then you put your voltmeter on the other end of the other side of the break, and you measure how much signal has come all the way around the loop back to that break point. In other words, you set up on the bench to do exactly what you normally would have done analytically on paper. Well, the trouble is when you start to do it on the bench, it ain't so easy. Because the first thing you have to do before you think of applying your AC test signal, the first thing you have to do is reestablish the DC operating point. And that may not be easy if your system has a high DC loop gain. If your system happens to be a regulated power supply, it has a high DC loop gain. That's what it's all about. And if you've ever tried to break the loop of a high DC gain system, you know what happens. You put the bias on the point where you broke it. What happens to the other end? Flaps around all over the place, wanders about and hits the stops. Something crashes against cutoff and saturation, and it's very difficult to keep the loop even in the active region, never mind at the right operating point. So it's very important to develop a method of measuring the loop gain in which you don't have to do that. The first thing is to know it can be done. Well, there is a technique which we'll talk about on Friday, which totally bypasses that difficult point. You can measure the loop gain without opening the loop. So that's a very powerful technique. An extension of that is sometimes you're real unlucky and you go and build your breadboard on the bench and it oscillates. So you'd like to measure the unstable loop also, because obviously something was wrong with your prediction and you need to get some guidance on what it was that was wrong so you can fix it properly. So you'd like to measure the unstable loop gain, again without breaking the loop. And it may seem as though that's paradoxical, because even if you could measure the unstable loop, it wouldn't be any good, because if it's oscillating, it's driving itself nonlinear. That's the only way it limits the amplitude of oscillation. So the model isn't the same as it is on your piece of paper anyway. So it turns out that a very simple extension of this loop gain injection technique can also be used to measure a loop which is actually unstable, and yet you still get the right answer. So that's a useful thing.
Do these things apply to simulation as well as bench work? These techniques?
The question is, do these techniques apply to a simulation as well as to a hardware measurement? Yes, indeed they do. And you can set it up in exactly the same way. Okay, so there's a couple of measurement techniques. Now there's one left. Iteration, which is, I already mentioned, comes about when the measurement now You've got them sorted out so you know the measurements are correct, but they're still not agreeing with your analytic prediction, so you have to go back and modify the model. Often, well, as an example, which in fact we'll do when we come to that point, often the thing that shows the discrepancy in the measurement is a frequency response. There's a drop-off somewhere at high frequencies, a pole, which was not predicted by your model because, of course, you started with the simplest model you could anyway, and maybe you left out some various capacitors. So you make a measurement and a pole shows up that you didn't predict. So you suspect that a certain capacitor needs to be added to the model. Often this is the collector base capacitance of a transistor, or the drain gate capacitance of a FET or something. That's a pretty common culprit for producing a high frequency pole. So what do? You go back to your circuit diagram and you put that capacitor in the model and you start all over again. Do the analysis from square one. At least if there's feedback in the system, that's what you have to do for the same reason as before. The whole circuit gets into it. So if you change the circuit by putting another element in, you have to do it all over again. And of course it's even harder this time because the circuit is that much more complicated. You've probably done that quite a few times too. And maybe also noticed that big chunks of that analytic derivation are the same as they were before, but not all of it. And again you get this feeling there ought to be a shortcut. There ought to be some way of not having to repeat the parts of it are the same and only finding the new part. That's what this last theorem does. It's back to analysis again, but it does exactly what that intent is. What it says is, if you've already found the gain of the system before you thought about this extra element, but then you want to put an element in other words, let the extra element be z, you found the gain when z was infinite. It wasn't there. And instead of going back to square one to find the gain in the presence of z, the theorem allows you to find only a correction factor, to multiply the answer that you already got. So you make use of all that work. It wasn't wasted. You've already done this factor in front. Finished. And to find the answer after you put another element in, all you have to do is find this correction factor. The correction factor includes the element z that you're going to put in there, obviously. It also requires two more parameters, labeled zd and zn. And I don't want to get into the details of what they are. Obviously, we'll do this when we get to talk about the theorem. All I need to say about them right now is that these two parameters are calculated on the original circuit before you put the extra element in there. So the way you use the theorem is the coefficient in front, the gain, you've already got. You've done that. You want to put another element in. All you do is you calculate these two parameters, zd and zn, which turn out to be driving point impedances of the original circuit at the same place where you're going to add the extra element. But they are properties of the original circuit. The extra element is not in there when you calculate them. So that's the additional work you have to do. You have to calculate those two quantities on the original circuit. And then all you do is plug into the formula. And the z shows up in this correction factor. Now the claim is that this saves you from calculating the whole thing over again in the presence of the extra element. There's no guarantee that that's going to be easier to use the theorem. But usually it is easier. If only because of the fact that you never do any calculation on the circuit with the extra element in place. The only additional work you have to do over and above the answer you got already is calculate those two driving point impedances. If it is easier to calculate those two parameters than it is to start over again with the element in place, then the extra element theorem is helpful. Let's say there's no guarantee that it is, but often it is, and that's all you can expect. It's certainly worth trying. There's another advantage of this result. The element z is explicit in this expression. In other words, it is not inside any of the other three parameters. So the correction factor itself tells you exactly what the influence of that extra element is. It's a low entropy expression because you can see the direct effect of that element. And there's lots of useful applications of that. One application is related to the one that I've used as the motivation to introduce the theorem, which is you've done all the work already, then you want to put another element in, and the theorem gives you a shortcut to the answer. Notice it's sort of like the input and output impedance theorem. You use the answer you got already, and you modify it. In this case, to find the extra element. Another whole class of application for this theorem is you know all the elements that are going to be in the circuit already. You know the complete system. And now when you come to start the analysis for it, instead of analyzing it all at once, which is what you normally do, designate one of the elements as being extra and throw it away. And analyze the simpler circuit. And then put the element back in using the theorem. And the potential benefit, again, not necessarily a benefit, but the potential benefit is that you've done 3 calculations on a simple circuit and you've never done any calculation on the complete circuit. And you see, you can stack that. You can throw away more than one element and put them back in one by one. The objective is to break down one huge, complicated piece of analysis into a sequence of simpler pieces. Again, no guarantee it'll be simpler, but it's worth trying, or at least worth thinking about it. So, that's the extra element theorem. And it's an analytic technique anyway, so it's back to the analysis part of the picture. And it's the last one on this list. And now what we're going to do for the rest of the time is go back over that list in more detail now. And already I think you can see that the philosophy behind this is the reverse of a lot of things that have been ingrained into you all the time. In fact, I've already mentioned this thing about approximation. What you should do from an engineering design point of view is the opposite of what you get told, which is put everything into the model to begin with, postpone approximation until you're finally forced to simplify something. So you're constantly fighting a rearguard action against overwhelming algebra. No wonder it goes into total paralysis. The engineering approach should be the complete reverse. Start with the simplest model as you possibly can, build it up later. Make every approximation you can as soon as possible, justified or not. Leave behind you a wake of assumptions and approximations, simplifications, strew them behind you. All you have to do is when you get to the final end, you've got to go back and check them, and you can't lose, because the worst that can happen is that some of them don't work, but you could probably choose a different one that would. Always keep the algebra as simple as possible and make it more complicated only as you have to. Build the answer. Move from left to right in that accuracy versus simplicity trade-off. Move from left to right gradually. Take too big a jump, takes too long to go back and check everything out. So that's the philosophy behind all of these things. And I guess you could summarize the bottom line of all that by saying that what we are told as students is the more work you do, the more credit you get. Wrong. Your manager would rather have an approximate answer tomorrow than an exact answer next week. That's because the economics get into it. Scott McNealy, the president, CEO of Sun Microsystems, gave a keynote address at the SIGGRAPH conference in Las Vegas last month. And he started out his talk by saying he came from the business end of the thing. He wasn't an electronics guy. But he made a related point, which I'm going to tell my students at Caltech from now on when we get to this point. He says that as students, we're all taught, or we all assume the objective is to maximize our GPAs. Certainly Caltech students work very hard at maximizing their GPAs. What Scott McNealy said he did, which was his own modification of that, he tried to maximize his GPA per hour. And see, that's a very important shift of position. That gets the economics of the value of time into it, which is one of the important ingredients of a practical design job. So, contrary to the usual student objective of the longer the analysis you can do, the more valuable it is, the students in my class get very upset when someone who turned in a 10-page solution gets a lower grade than someone who turned in a 2-page solution, because they think it ought to be graded by weight. See? And I've discovered it's extraordinarily hard to get them to reverse that way of thinking, which is not surprising, because that's really how we get taught. But you see how it relates to the real life design problem. The problem is, get an answer any way you can. Then you go back and fix it up. You modify it, you extend it, you tweak it. The wrong way to start is to put everything in first and simplify as required, because that's always a rearguard action. And that's what happens when you throw it all into the computer. You put it all in. At least the tendency is to put it all in for the same reason, because you think the computer will give you an accurate answer for everything you put into it. And the point is not just that it may not give you the accurate answer. More important is the fact that even if it does give you an accurate answer, what are you going to do with it? Because it doesn't give you any help when you need to change things. The computer really, as it is at its most valuable, near the right-hand end of that accuracy versus trade-off picture, which is really when you've actually completed the design. And all that's left to do is worst case. Computer is very good at doing that, because it requires a lot of computation very quickly. But that's a matter of tweaking the final result. The design process may even have been slowed down if you put it all into the computer too soon. Because the inaccuracies that the computer may have put into it, you also have to subtract out as part of one of your iteration loops, which means that you've got to work harder than necessary. So what I've set up to now is basically the motivation for all of these techniques. And that's the end of the introduction, and that's a good stopping point for a break.